Alright, so with number 8 here, now we're taking a look at this one. Notice that it's already written in terms of y. That's an indicator that you're probably going to want to use dy for this. Now they will not always give it to you in terms of y. Sometimes you have to rewrite the equation to be in terms of y. But if they give it to you in terms of y, most likely you're going to want to do it in terms of y. When we take a look at our function, we can see that if I were to do it with respect to x, that this would have been my top function, or part of it, and this would have been my bottom function. But then, for this next piece, I would have had to solve for y, which means I would have had a positive and negative square root. So this would have been my top function, and this would have been my bottom function, positive square root and negative square root. So a lot of pieces there. If I take a look at it with respect to y, then this is always the right function. So again, if you kind of turn your head to the right, this would be like my top function. So it's the right function minus my bottom function. That does not change, which is why dy is going to be more advantageous for us here. So again, everything needs to be in terms of y, which means your bounds need to be in terms of y. So this black line, this black curve here is my right function, and that is this here. And then we have just a line negative y, which is this guy. So my right function, I'll go right up here. My right function is 2y minus y squared minus my right function, or sorry, my right function minus my left, so my left function is the red one, negative y. Now once again, our bounds need to be in terms of y. So when we find our intersection points, we see that that's from y equal to 0 and y equal to 3. Again, you want your y values for this, not your x values.
How do you know how to calculate?
So for this one, you would probably have your calculator for this, but if you think about it, if this was just a normal like x squared, it would be a parabola of some sort, and that's been reflected. So if you think about when you turn your head kind of sideways, we have a parabola that's been flipped upside down. What would be easier to do if you didn't have your calculator for this is go ahead and get it in terms of, or go ahead and solve for y. So I would have, well, this one's not quite easy to solve for y, is it? So we've got, factor out a y. So you could then think of just if you substitute in values. So if I take, like, set this equal to 0, when x equals 0, my y value would be 0, and is that positive 2? So then those are like your, instead of your x-intercepts, you know, your y-intercepts, if you would. And then, like we said, we know that's reflected upside down like that. So again, guys, when you're thinking of your graphs, particularly for your y's, it's kind of like the x graph, but turn your head sideways. Kind of a plot of that. Other questions with number 8? When in doubt, just plug. Also, just when in doubt, plug in points. Plot those. So again, if we're doing in terms of y, your functions must be in terms of y, and your bounds must be in terms of y.
Can you go over like getting the two y dx to things like the c dx, to like get it so that it's a left and right?
You mean like choosing dy versus dx?
Yeah.
So you get to pick depending upon what's advantageous for you for this one, because my right, if I try to do it up and down, so if I try to do it with respect to x, and that means I'm going to do everything up and down. So this would be my top function for part of it, and this would be my bottom function. But then, once I come past here, it changes. This is my top function, and I now have a different bottom function. So we could do dx, but you're going to have to rewrite this in terms of x, and you would have then this integral plus this integral. So you can do it that way, it's just you're going to have two different integrals.
Like for d functions.
So we're just integrating like normal, but y is not my variable I'm integrating. So instead of so normally, like this guy over here, when I take a look at my integrals, everything's in terms of x dx. So now it's just my variables are y dy. So you're going to integrate like normal, but y is your variable, and you're doing like power But you get to pick dy dx based upon the graph, which one's easier. If they give it to you in terms of y, most likely to do dy.
Did you say that we could just plug it into the calculator, replacing x?
Yeah, so when you're doing it on the calculator, because your calculator won't let you substitute in y here, so you're just going to do everything in terms of x dx, and it's going to give you the same one. Your calculator takes into account, like we could have put in t's, we could put in j's, but your calculator designates x as a variable, so in your calculator you just write 2x minus x squared minus negative x dx. Alright, other questions on the homework? Show me thumbs up, thumbs down, thumbs down how you felt with this topic. Okay. It's not meant to be a terrible one. What we're going to do is build upon this today to talk about volumes with rotation. So what we're doing today now is we're saying, okay, so let's go ahead and take this region here. It's right now just a 2D region that's shaded in. Well, let's now take that region and rotate it around the x-axis, or rotate it around the y-axis, or maybe around the line y equals -2. And then that gives us a shape. So if I were to take this and rotate it around this line here, then that's going to get me a shape that looks something like this. So we're now getting 3D shapes, and instead of just finding the area of that region, we're going to find what's the volume of that 3D shape that has been created. So we're building upon this. Let me go ahead and pass out the notes for you, and then we'll get going. Alright, so take a look at what I have up on the board here. So this is a nice little region here, just our square root of x curve, nothing too crazy here. And I'm taking a look at the region from A to B, so just the shaded region here. I want you to go ahead and draw somewhere on your notes or just on the back of your assignment sheet. If I were to take this region and rotate it around, let's just go rotate it around our x-axis here. So if I were to take this shaded region and rotate it all the way around 360 degrees, what would your shape look like? Okay, so taking this region here, rotating this around, what would your shape look like? I know I'm asking you to draw 3D shapes here. It's not going to be beautiful. Do your best with it. What would this look like?
Like that.
Oh, you mean like if we were like pushing it back?
Yeah, it's like this is a panel and it's getting turned all the way around 360 degrees. Would that look? It's if we were looking at like this. Yeah, that's a good way to think. So do your best, draw a picture what you think that's going to look like, and I'm going to have you compare it to shoulder partner.
There's already.
Well, I'm going to change it in just a moment.
Wait, it's just in the
All right, let's see how you did. Now, again, I'm only rotating this portion of it, but did you get something that looks like this?
That's pretty cool.
So we've got like a solid cone-ish type thing, cone-ish cylinder type thing. Okay, now let's change it up. Let's go ahead and change it. What if I'm rotating around this? We're going with approximately y equal to 2. So once again, I'm taking this region. Ooh, that's a good description. It's like the magic bullet cup thing. That's, I like that. Yeah, that's good. Like the magic bullet container. Okay. So now I want you to draw a picture of what you think this shaded region rotated around this line now. Listen up, guys. Listen up. I'll let you get off your phone. Take this region and rotate it around this line here. So notice, what do we have in between? There's space. Keep that in mind, right? Do your best to draw a picture what that's going to look like.
Wow. It just we're so smart, guys. Perfect replica. Tonight, but
All right, bring it back up front. Quiet down. Let's see how you guys do this one.
oh my god, wow, we were right.
So now we have kind of that shape, but with the gap in the middle. It's like a cylinder has been taken out of our magic bullet. Good. All right, let's just do one more.
It's like an extended donut.
What if I go above up here?
It's gonna look like a little,
No, there's no picture.
Ah, there's no picture for this.
No.
All right, so I want you to, on your assignment sheet or somewhere, draw a picture of what you think that would look like. It's a little different.
How am I supposed to draw this? I'm really confused. Actually, it's not. Where's mine? I see.
Alright, I want you to share your picture with 2 other people.
I don't know how to do that.
That's like the column inside of that.
You can't even fathom it. I'm so tired, dude. My face is itchy. I was talking to my counselor. It's due in 10 days.
Alright, bring it back up front, please. So we're done with this. Alright, I want to see your pictures. Go and hold them up and let me see. Let's see what we've got. I see some good ones. Alright. So let's take a look at this one. Now, as some of you guys realize, the easiest way to visualize this is to kind of think of its reflection. So I'm going to take this and think of this picture reflected across. So would you agree that it would look something like this? Right? So I'm just taking that and reflecting it above because it's going to be a mirror image on top. And then I just have a nice circle there and a nice circle there. So we have the edges here, our straight edges. And then we have kind of this funnel cloud that's been cut out. See that there? Let's go ahead and take a look at the picture that the program does because it works so much nicer. Yeah, so we have all along here our circles that are being cut out. Right? This is going to be one big circle and taking out that middle piece. All right, let's go and take a look at the program.
Can you erase this?
Yes. So again, we can see that funnel cloud has kind of been taken out of it. So it's like a cylinder with that funnel cloud shape taken out of it. So these are the different shapes that we're going to be taking a look at. Now we see that there are different, okay, I need to pause, I think it's just getting darker and darker. No. Alright, so as you can see, the shapes change based upon how we're rotating. We use that same graph, but it changed depending on if I was going around my x-axis. How was it different if I went around my x-axis as opposed to anything above or below?
It just won't have that in your circle.
Yeah, so when I did around the x-axis, then I had it, there's no gap there in the middle. But when I went ahead and took it somewhere, oops. If I put it below, if I put it above, we're going to have that gap right there. So again, this is what we're doing. We're taking the idea of that region between two curves, and now we're rotating it to give us a solid. We're going to find the volume of that solid. So with, just like we have with our regions between two curves, we can do it with respect to x or respect to y. Our region or our volume is going to change the shape even if it was with respect to x or respect to y. So I want you for your last one here, take this region. How would that change if I did it around the y-axis? So if I went around my y-axis. So try to draw a picture. Envision this, it's like a fan that comes all the way around. Rotating.
Those games where you like throw a coin down and then you know those little person.
So I want you to go and draw a picture what you think that would look like. Yeah. Within it, not in the we will not have that within it.
I think so. Probably. I'd rather have this year than this.
All right, bring it back up front. Let's go ahead and see how it changes. I'm going around our y-axis. So it's kind of similar to that last one that we did, where it's, again, that cylinder that has been rotated around with that kind of cone shape being cut out. Okay?
Why are there three?
They're just showing, because there's that center gap there. Let me reset. So guys, notice we have this center gap here, so as it gets rotated around, there is going to be a gap in the middle there. That's just that third one, they're just taking that X and turning it around there. So we have a nice cylinder with this cut out of the middle as well. Okay. All right, so that's what we're taking a look at for today. So go ahead and Whoops, that's not what I was supposed to do. Pretend that didn't happen. So just real quick, let's recap what integrals are. Back when we first learned integrals, we talked about how, let me bring it back to our original problem here. When we first learned integrals, we talked about how an integral is really taking a bunch of little rectangles, finding those areas, adding them up together, and that gives us our integral. Now we start off with Riemann sums, where we would find all those little rectangles. And integrals where those rectangles we're approaching an infinite amount of rectangles, and thus the width is infinitely small. So trying to get that approaching 0 and adding those all up. Now, when I do my rotation here, let's bring our axis of revolution back down. What type of shape do I have here? If I were to do a cross section, if I were to cut this volume down, what type of shape do I have? It's circles. It's like a disc. So when we're doing our volumes here, what we're actually integrating is no longer little rectangles, but circles. And we're taking all these circles and adding them up together. So what is the area of a circle? Pi r squared. That was a little not as confident as I was hoping you guys would say it. Pi r squared is indeed the area of your circle. And so you'll notice with our formula that we're about to do that we're integrating the formula pi r squared. Again, the idea is that as we cut, we're cutting off just a bunch of little circles, and we're taking those areas and adding them together to get our full area there. So again, it's the same idea as the integral was. We had a bunch of rectangles, and we were trying to get, as we got more and more rectangles, it got more accurate. So we increased our number of rectangles, and we're decreasing that width. Same idea here. We increase the number of circles, and we're decreasing that width. So we're integrating that area of the circle pi r squared. Okay. Now, when we take a look at that one where we have the gap, so reset. You guys said that the big difference here was that we now have that gap in the middle. So as we can see, we're integrating still that area of the circle, but I need to take away this middle piece that has no volume with it. So we have the outside, this big circle here, and I have all of this area in here, but I don't want that middle value. I don't want this piece of it. So how would we find, if we had a circle like that, how would we find this area here? What would we need to do? Yeah, we would just need to take out that middle circle from the bigger one. And so you'll notice on your paper you have what's called the disk method and the wash method. Our wash method is when we have that hole cut out. You guys know what washers are, like not the kind that wash your clothes, but the metal pieces, and put it with a nut and bolt. So that's why they say disc and washer, just because the cross section, that chopping it down, that's what it's going to look like. I kind of like to think of it as a donut, just because that's more exciting. But again, for our wash method, we're going to have to take the larger area and subtract from it that area that we don't need. So that's why you'll see a pi r squared minus pi r squared. But we'll take a look at this. Okay, questions on what's happening with this? Honestly, the hardest part of this is just getting the setup, and I'm kind of visualizing what's happening, but hopefully we're seeing some done beautifully by the program that helps you kind of get an idea of what these different types of shapes will be. Okay, so let's go and take a look at your notes. Okay, so a big old huge paragraph that you can read if you'd like to. Again, what this is saying is that our integral is defined as the sum of all of our little cross sections, and now our cross section is the area of a circle pi r squared. So our area of a circle pi r squared is what we're integrating. Okay, so again, if we have our disk method, then that's where we don't have a gap. Where when we rotate this around, this is one solid mass. This is all just one big solid mass here. Okay. So when we take a look at our cross section, we have a circle. And we want to know, again, the area formula, so pi r squared, that's what we're integrating. So if I were to integrate pi r squared, and we're going, for right now, these are with respect to x. How is this different than this guy here? What happened? What are those two formulas?
It's going to be a pi over 2. I mean, pi over 3.
What happened with our pi here? We just pulled down front. Why can we do that? It's just a constant. Yeah, it's just a number, so we can pull that constant out in front. You're more than welcome to leave it inside, but I think most people, when they see pi, they try to do power rule with it, so I would recommend just bring it out. Okay, so again, our r, this is our radius of the circle. Well, my radius of the circle is just going to be whatever that function's height is. So for our example that we had where it was that square root curve, then this height would just be square root of x. And it's of course going to change depending upon where you are within your shape here. But square root of x will model whatever those heights are. Now, once again, we can do this with respect to y. Keep in mind that if we do with respect to y, our equation here needs to be in terms of y. And our bounds need to be in terms of y. Now, they will prompt you, they will give you information to know that you are to do it with respect to y, because your shape will completely change depending upon whether you do it with respect to y or with respect to x. So it all depends on what your axis of revolution is. They'll tell you what line to revolve around. Yes?
So how do you know which circle we need to find radius axis to be?
So it's the radius, it's going to be the same radius all the way along here, because our radius will be based upon the function, square root of x. So over here, my radius is still square root of x. Here, my radius is still square root of x. Here, radius is still square root of x. Now, of course, at this point, say it was 2, then be square root of 2. Here, it's square root of 3. But because this is a function, it has the variable x, then it will change based upon where you are within your function.
I'm still confused as how you got square root of x.
I'm saying that for our example that we did, we had square root of x was our function that we were looking at. And that's the region that we were rotating. So for that particular example, our radius of that circle would just be the height of the function square root of x. So it's going to change depending upon which function you have. All right, other questions so far with that? Now, as we saw, there is also situations in which we might have a gap. It's not always going to be a nice perfect gap here, where we have a nice cylindrical gap. It could be wavy, but what we have is, again, like we talked about, our outside piece and our inside piece. So that outside piece is going to be that larger radius. So we always go from our axis of revolution. So we always go from the axis of revolution, and that's going to be my outside radius there. Now, again, this is going to be dependent upon your function. And so you'll notice that we'll be using that top minus bottom, so top function minus bottom function, just like we did last class. And then we want to subtract from there the area based upon my little circle here, which is going to be my little r. Okay. So they've written it this way, where it's pi times the quantity of our integral r big R minus little r. We can rewrite this, and I want you to go ahead and write this in your notes here. So pi big R squared dx minus pi little r squared dx. Because again, this is going to be my outside or my big circle. And this is going to be my inside or that gap. Kind of where we have that hole. Now they went ahead and said, hey, since it's just pi times r squared, they factored out the pi. But it might be easier for you to think of the radius of the big minus the radius of the small. The biggest mistakes that students make with this, they forget their pi. So keep in mind our cross sections are circles, so we need that pi. And they forget the square. The the area of the circle is pi r squared, so don't forget your square. Okay. questions with this before we move into actually doing it?
Sorry, in the first one that they give us, they have bounds, but you didn't draw bounds, does not matter. It's
So
the same.
it's going to be the same bounds, yeah, because we're going our outside radius and our inside radius will have the same bounds, so it will be the same bounds. So we'll just say A to B. And once again, if it's with respect to y, that will change the shape. So notice dy, our radiuses must be in terms of y, and our bounds must be in terms of y. So for this particular shape here, what we have is this little region is what's getting rotated. So we end up with this shape. It's kind of right there. So again, it's kind of like the magic bullet with the cylinder that you have.
If we're rotating on the y-axis, where would C and D be?
It would be your heights of your radiuses there. So you would go from your axis of revolution out to your height. And we'll do a couple of those. Other questions with this? Okay, so let's just go and take a look at our first example. Now, you, depending on how you are, you might want to draw your pictures on a separate piece of paper. I feel like the boxes are kind of small. So we're going to be drawing pictures of our region and what that rotation looks like. So if you need separate sheet of paper, feel free to grab one and do that. I'm going to go ahead and see. Alright, so our first one here, it says find the volume if the region enclosing y equals 2x, y equals 0, and x equals 3 is rotated about, and then we have different scenarios here. So just like we last class, we need to go ahead and set up a region before we can take a look at what it's going to look like being rotated. Alright, so we have y equal to 2x, y equal to 0, x equal to 3. So 1, 2. Alright, so my line y equal to 2x starts at the origin. And we're going from 1 up to 3. Alright, so I've got my line here. Now that extends, of course. We want to enclose by that line, y equal to 0. And x equal to 3. Okay, so we've got this region in here. Go ahead and shade that in. And this is the region that we're rotating. Okay, so once again, they're going to give us a region. It's going to be made up of certain functions, certain lengths. And we're going to take this region, and this is what we're rotating. So we're going to take this region and rotate around these different scenarios here. So our first scenario says around the x-axis. Let me go ahead and bring this up a little bit so it's easier to work with. Okay, so I'm rotating around the x-axis. I feel like the easiest way to go ahead and draw a rough sketch of this is to first reflect that area. Okay, so I'm going to go ahead and just reflect that down. And again, I'm rotating it around. Now, when I go to rotate this around, am I going to have a gap in the middle? No, there's going to be no gap here. So I have pretty much just a nice big shape here. What type of shape does that end up making? Yeah, nice cone. Pretty basic, nice cone here. Alright. So we need to establish what our radius is going to be. Now, since this is disk, I don't need that smaller arc because there's no inside radius that I'm cutting out. There's no gap to take out. Alright, so I just need to figure out what my radius is. When you establish your radius, always go from your axis of revolution to the curve or the function. Okay, so I'm going to start at my axis of revolution. We're rotating around the x-axis. And then I want to go to my function. Always go to your original function, not the reflected one. I mean, you can go to the reflected one, but then you're going to have to figure out what that equation is, and you might have negatives, so just go to your original function. Alright, my radius is from here to the top of my function.
So we can't try that and say it's 6.
we know what it is at that exact point, but I want to be able to write with that radius no matter where we are within our function. So if you'd rather, you can draw like here in the middle. Does that make sense? I know that my radius here is going to be 6, but what is it at 1.75? Okay, so my radius for this particular problem is just the height of my function. What was that function there? 2x. Okay, so again, going from my axis of revolution to the edge of my solid here, the edge of my circle, if you would, is just the height of that function, 2x. Okay? So now we just go ahead and set up our integral. So our volume is pi, the integral of our radius squared. So quantity 2x squared dx. And we need to figure out what our x values are, our bounds. So again, we're doing dx, so with respect to x, we started at 0. And how far did we go to? 3. Good. So our volume is going to be pi times integral of our radius squared. Again, do not forget that squared there. Don't forget your squared. Don't forget your pi. All right, questions on that setup?
Is the radius equal
2x. So our radius is we always go from our axis of revolution out to the edge. Now, it's going out to the edge is always going to be the height of whatever my function was there. My function was 2x. So that radius, that height, is 2x, wherever we are within our curve. All right, I want you guys to go ahead and integrate that by hand. See what you get. And once you've integrated that by hand, then check it on your calculator. I want you to integrate this one by hand. It's not too long. So again, once you've done it by hand, double check with your calculator that you did it correctly.
Will this be a calculator question?
It could be. I would imagine one like this is probably a calculator problem.
So then will we just say 36 pi?
You would leave it in terms of pi. Alright, so leaving it in terms of pi, what do we get for our answer?
36 pi.
Good, 36 pi. Now Tiffany was asking, is this going to be a calculator or non-calculator question? Honestly, guys, it just depends on the problem and the year and what they feel like. Sometimes they're calculator, sometimes they're not. This type of problem, I wouldn't be surprised if it was non-calculator because it is a pretty basic integration. Leave it in terms of pi unless it directly asks for something else, but pretty much all non-calculator questions would be left in terms of pi. If we didn't leave in terms of pi, what do we get for our answer? Is it like 113 something? 0.97. Okay. Also, if it says sleeve in terms pi and it is a calculator question, I recommend just evaluating the integral without the pi, and then just stop the pi at the end. Okay, now again, I don't feel like I've ever seen AP ask for it to have units with it, but if it did ask for units, it'd be units cubed, because we are talking about volume here. Again, I've never seen them ask for it, but you never know what they're going to throw at you. And hopefully if they ask for units, they actually gave you something more than just units. Okay, questions on our setup with that? Okay, so let's take a look at our second one. Again, we're taking the same region, but now we're rotating around the line y equal to 6. So before we start drawing, take a look at my original graph. Where is y equal to 6 in relation to my graph here? It's above it. Good. So you'll notice that for the rest of these, the boxes, well, second the y-axis, the boxes are blank so that you can adjust your axes as needed. I'm going to go ahead and just squeeze my axes here on the edge. And it's rotating around the line y equal to 6. All right, so I'm going to just kind of redraw the shape here. Now, if I'm rotating around the line y equal to 6, I'm going to need to have enough space to reflect it above. So just keep that in mind. We probably want about a height of 12 there. And it doesn't have to be exact. We're just trying to get an idea of the visual there so we can establish what our radiuses are going to be. All right, so again, I know we have a point, what was that, 3, 6? Okay, so again, I'm using this same region, the same shape here. And now I'm rotating along this line y equal to 6. Okay, so once again, just draw a rough sketch, a rough reflection of what that looks like. So I have this, something like that. And we're going to have it gets rotated around. So I'm going to go. Let's use So again, we can see for this one, we now have kind of the outside shape kind of looks like a cylinder, right? And then we have that cone cut out of it. All right, so here, do we have a gap? Yeah, we definitely have a gap. And you want to just look to see, is there a gap anywhere within your solid? We definitely have a gap. So we're going to have the washer method, both big R and little r. Okay. So let's go ahead and establish what those are. Alright, so my big R. Again, I'm going from the axis of revolution to the furthest edge of my region there. Now, you can go either way. I highly recommend you go to the function, though, just to make your life a little bit easier. So I'm going from the axis of revolution to the edge of my shape. I'm going to go down since that is where my original region was. What is that height? What is that radius? What's that number? 6. 6 the whole time, right? No matter where I go inside of here, that is a height of 6. So my big R is just 6. You can say 6 minus 0 because it's going to the x-axis there, but just 6. Okay, so that's my big R. Now we've got to figure out what that little r is. This little itty bitty guy here. What is that little r going to be? Talk with your shoulder partner. What is that little r going to be? So again, in case you didn't see when I drew it, going from my axis of revolution down to my inside region. What would that little r be?
Why would you choose that point to make the
it anywhere along here. You could go with
Just to 3, all the way to 3.
You could do it anywhere along here. But we're going from our axis. We're going from our axis of revolution. I'll get rid of my big R's.
So the small one function.
It changes, right? So it should be based on a function. So this would be like my little r. Notice how my little r
So
does
he's like
change.
trying to call her back.
Does that make sense?
Just pick her up from me, and I'm like, yeah, sure. So I just
It is
picked
the
her up.
equation.
Yeah, I know. Usually we have.
All right, who feels confident that they think they know what this radius
She
is?
didn't scratch me.
Wants to give it a try. Go ahead, Rachel.
6 minus 2.
Yeah. 6 minus 2x. So our big radius, we said was 6 because we're going, no matter where we are for a big radius, it goes to the outer edge, so it's the height of 6. But now for our inside radius, notice that it changes. It goes from my axis of revolution down to my function. Now, once again, it's really top minus bottom, because that top height would be 6, and we want to subtract away that height of 2x. And now Hunter asked a question, said this is going to be a function, isn't it? And it is, because it changes depending upon where we are. So we're not going to have just a constant 6, because it's not the same radius of 6 the whole time. It changes it. So again, so our big radius we said was 6. And our small radius was 6 minus our function of 2x. So you can see we're applying that property of top function minus bottom function. Okay, questions on that? That's really the hardest part of this, then we just do our integral. Okay, so we have our washer method. So again, we have 2 different integrals. So volume equals pi times the integral of big R squared, so 6 quantity squared, dx. What are my bounds for this? 0 to 3. And then I want to subtract away from there that gap. Whoops, I lost my pi. Don't lose your pi. So minus pi little r squared, which is the quantity 6 minus 2x. Still from 0 to 3. Now, again, you could write this as 1 integral pi times big R squared minus little r squared. But either way. Okay, just use your calculator for this one, see what you get. Let's leave it in terms of pi. So basically, do your integrals without pi, and then that answer is times pi. Double check with your short partners if you get the same volume. Alright, did we get 72 pi? Anyone get 72 pi? Good. Alright, and again, we can put it in decimal form. So if we did it in decimal form, we'd have 226.195 or 195. Alright, questions with this? Now, again, a couple of techniques for you for the AP exam. On the AP exam, they are most certainly not going to prompt you with big R squared, little r squared volume. They're going to give you no promptings whatsoever. But you may want to go ahead and establish big R equals and little r equals. Because once again, if you establish that, then in your integral setup, as long as you have defined it, in your integral setup, instead of saying 6 squared, you could say big R squared. And if you've established that little r, is that little radius there, then you could say little r squared. And then you get your points for the setup, even if you messed up your integration. Okay, but you have to establish, you have to define big R as 6 and little r is 6 minus 2x. You could once again say f of x, g of x. You would say y1 equals y2 equals. And I would recommend in your calculator as you're doing this, go ahead and put big R as y1, little r is y2, or vice versa. So then when you're integrating, you don't have to retype out that whole function. Now, of course, it's going to change, your radiuses are going to change based upon the problem. But those are just some techniques you can use. So again, you have to define big R as your radius. You have to say let R equal and let little r equal in order to use this method here. But you can at least then get your points for the setup without losing any points. You might be a little less likely to lose your square, a little less likely to use your pi. The biggest way that students lose points is that in their setup, they either forget their limits, they forget their pi, or they forget their squared, unless you don't get any of those setup points. Okay, let's go take a look at C. What's different between C and B? What do you say?
2 units up.
Yeah, it gets shifted even more. It gets shifted even higher up. So, again, I'm going to stick to using my axis here on the edge. I know my shape has the point 36. And now I am rotating around the line y equal to 8.
Oh, wait. Is it different? Is there
Okay, so once again, I'm just going to get a rough sketch of what it looks like. So I'm just reflecting that shape. And as I rotate this around, do we have a gap in the middle for this? What do we got? Oh, without a doubt. It doesn't look beautifully symmetrical. But again, it looks like a cylinder with more than a cone cut out of it there. Okay, so let's go ahead and establish our big radius. So always go from your axis of revolution to the outer edge of your original region. What's my big radius going to be? Good, a solid 8. It does not change. All the way along, my edge, my outside edge stays the same at 8. Okay? And then let's take a look at our inside radius. So again, my inside radius from the axis of revolution down to our function itself. What is that little r going to be? 8 minus 2x. Again, top minus bottom. Our top function is 8, bottom function is 2x. 8 minus 2x. Questions on the setup there? Right. So our volume once again will be pi. What are we going from? What are our bounds?
0 to 3.
Still 0 to 3. Big R squared dx minus pi integral from 0 to 3 of little r squared dx. Alright, go ahead and punch out your calculator, see what you get. I like terms of pi, so let's leave it in terms of pi. Let's see what we get. did we get? Good, 108 pi. Okay, questions with that? Okay, now let's take a look at revolving it the other direction. So let's take a look at D. It says revolving around the y-axis. Same region, but now revolved around the y-axis. Alright, so once again we have that region as the point 36. Alright, so we are now rotating this around the y-axis. So same idea, you just want to get a rough reflection of it. And we know that our shape is going to be rounded on the ends. And it's going to be the same process, just now we're going with respect to y. So once again, we can see it looks like a cylinder with a cone cut out of it. Give you a moment to finish your pictures. Okay, so everything needs to be in terms of y since we're revolving around a vertical line. So we're revolving around the y-axis, that's a vertical line. Everything needs to be in terms of y. Do we have a gap? Yes. So we will be doing wash, we have two different radiuses. Alright, so let's first establish our outside radius. The y-axis is my axis of revolution, so I go from there to the outer edge of my original shaded region. Does that change? No, that's the same radius all the way through. What is that a radius of? 3. Good. Okay. Now, let's take a look at our inside radius. Does that change as we move up and down? Yeah, that does change, so we should see the variable in there. Now, we know that this is the line y equal to 2x, but I need it in terms of y. So my line was y equal to 2x. How do I get this in terms of y? What do I need to do? Yeah, just divide by 2, solve for x. So I would get x equals 1/2 y. So would you agree that this line here is just the line x equal to 1/2 y? Would you agree with that? Okay. So keeping that in mind, what is my radius, my little r, going to be here? What'd you say? Good. So again, it's in terms of why you want to think right minus left. Just like we do with the area between the two curves. Right function minus left function. So my right function was just that vertical line 3, x equal to 3, minus my little function here, so 1/2. So I know again that this entire length would be 3, and this would be the 1/2 y. So if I subtract that away, that gives me just that little bit there. Okay. Questions on establishing our radiuses with that? All right. So now let's go and set up our volume. So pi integral. Ooh, what are our bounds here? Good. 0 to 6. My big radius. And we're doing it with respect to y. And then again, I want to do minus pi integral from 0 to 6 of my little radius with respect to y. Don't forget your square root. So make sure, once again, each time, that you have your pi's squared. Pi squared. And again, as long as you've established big R equals little r equals, you can say pi big R squared dy, pi little r squared. Okay, go ahead and use your calculator to figure out what this one is. Again, let's leave it in terms of pi. Remember, when you're entering this in your calculator, you're just going to put X is where you see Y, so it'll calculate it for you. Alright, did we get 36 pi? Questions on that? Okay, let's take a look at one more. Alright, so round the line x equal to 3. What type of line is this? It's a vertical line. Good. Okay. So take a look at my original picture. Wouldn't x equal to 3 be this guy here? Okay, so we're taking this region and rotating around like that. So just so you have an idea of what you need for your axis there. Alright, so I have, again, my shape was we're rotating around this line here. Ah, this will be pretty cool. So this is my region. And I'm rotating it around this guy. So again, just a rough reflection. And when I rotate that around, what type of shape does that make? A beautiful ice cream cone. Upside down though, I'm not sure what happened to the ice cream. It's a nice cone here. Do we have any gaps? No, so we're just going to be doing our disc method, just the radius. Just the big R. Alright, so again, always go from your axis of revolution to your original curve. Axis of revolution to your original curve. It'll make life easier, because if you tried using this other side, you'd have to figure out what line that is. Alright. What's my radius, my big R, going to be for this? 3 minus what? 3 minus 1/2 y. Again, we're doing it in terms of y because it's a vertical rotation, or we're rotating around a vertical line, so it always has to be in terms of y for that. So again, we're looking right minus left. This would be my right minus my left. So my right would be 3 minus the 1/2 of y, which is 3 minus 1/2. And then we don't have a gap, so don't have to worry about that. Questions for radius for that one? Yeah. So my radius, there's no gap. We always want to go from the axis of revolution to the function. And so we want to think, because we're in terms of y, right minus left. My right would be 3 minus my function is the 1/2 y. So if I had 3 would be this whole radius, and I want to subtract away from that. So 3 minus the 1/2. Yes?
Would you be able to find the volume just by finding the volume has 2 columns?
Yeah, you could actually, because you could figure out what your base is. Yeah. Alright, so our volume would be pi integral of big R squared from 0 to 6. Okay, questions on that one? Okay, your homework. Sorry. There is a lot of extra practice, right? I'm not going to make you do all of that. See where it says homework? That is required. The pages that say homework and afterward, before that is extra practice as needed. So basically that last page from back. I almost said have a good weekend. Have a good day. You're going to Stinger 5.